Okay, so we consider a small oscillation about the position of a stable equilibrium. We have just 1 degree of freedom. Now, a stable equilibrium for us corresponds to a point where like U of Q is minimum, and clearly uh, a movement away from this point sets up force minus du by dq, which leads to the which tends to return the system to equilibrium position. We assume q equal to q naught to be the equilibrium value of the generalized coordinate. Now what we do that we expand u of q around q naught. So we get this value u of q minus u of q naught as half of k square q minus q naught whole square. This is because we assume del u by del q to be 0 at the equilibrium point, because at the equilibrium point this is minima, and so this thing is 0. Basically it's 0 because it's the equilibrium point, and we just get this term half of del to u by del q square into q minus q naught whole square. Now we assume k square to now we take k square to be del to u by del q square. So taking the deviation to be x, we write u of x as half kx square. Now we assume that if the kinetic energy of the kinetic energy of such a system will be of the form half into a of q into q dot square, which will be same as half of k into q a of q into x dot square, because x is nothing but q minus q naught. So further we make the approximation and we say that if the x and if the order of x dot and x is same, then half of a of q will be same as approximately half of a of q naught, and we write a of q naught as m, which need not be mass in general. We use the term m here. So we get this Lagrangian half of m of x dot square minus half kx square. Equation of motion from here can be derived using Euler-Lagrange, which you will get as x double dot plus omega square x equal to 0, where omega square is k by m. Now you write it in terms of cos, like there will be two independent solutions, cos omega t and sin omega t. The general solution will be the linear superposition of these two solutions. If you can further add the vectors, add them vectorially or something, and you can write this thing c1 square plus c2 square as a square, and tan alpha will be minus c2 by c1, where you will call alpha as the phase and omega as the angular frequency. Further, the energy will be half mx dot square plus half kx square equal to half m omega square a square. An important remark here is that the omega is independent of the initial condition, and basically it does not depend on the amplitude, and evidently as it turns out this is the only kind of motion where the omega is independent of the initial condition, or basically the time period is independent of the amplitude. Now you can do the complex representation of the whole thing using x equal to real part of exponential I omega t, and invoking linearity. You can basically take the real take out the real part, and basically you can do the real part at the very end, because if all of your operations are linear and all, so basically the real part and the complex part.
Now you're even losing your clarity for speed. I mean, at least be clear. You're just
okay. Okay.
It's okay, but you should at least make some sense. Okay, go.
Yeah. Okay. So now let's talk about forced oscillation. The forced oscillation or the oscillation where there you have some external driving, and also we assume that the oscillations are small, so the corresponding field will be weak, and which I don't really understand. Now finding the new Lagrangian, we try to find the new Lagrangian for this particular case. Besides the existing half kx square term, there will be a term coming because of the coupling with the external field, and so you will have u external xt as you basically write an extra u external xt and expand it in the power of x. So you will have one term which will depend on time, then there will be which will be only depending on time, and then this first order derivative on x, and then higher order things. Now you assume only since you assume the oscillation to be weak, we take here only terms up to first order. Furthermore, this term will not contribute in the equation of motion because it only depends on time and time only. Now we call this minus del u by del x at x equal to 0 to be ft, and so the energy associated will be minus x of x into ft. So Lagrangian takes this form. Equation of motion for this one will be x double dot plus omega square x equal to ft by m. Now you can clearly see that as it was in the earlier case also, you can write it in you can write the solution as
small question. Sorry for interrupting. Why was it that you can drop the first term if it's a function of time only?
Yeah, because if it's a function of time only, then there will be no contribution coming from, there will be no contribution by it in equation of motion or Lagrange, because there you do del u by del q or del u by del q dot, and since u is a function of time here only, so del u by del q will be 0, and so no contribution in the Euler Lagrange.
Okay, thank you, Kishore.
Okay, so we write now we try to solve this. Now the way you solve is that you write the homogeneous solution, and you superpose the special solution over the homogeneous solution. Now you take the a special case to be if ft equal to a small f cos gamma t plus beta, we try equal to x1, we try x1 equal to v cos gamma t plus beta. When you substitute it in the differential equation, you will find b equal to f by m omega square minus gamma square, and so this x equal to a cos omega t plus alpha plus a small f by m omega square minus gamma square into cos gamma t plus beta is the overall solution. Here a and alpha are determined from the initial condition. Now what we see, we try to look at what happens near the resonance. Near the resonance, your x will be a dash cos omega t plus alpha plus a small f m omega square minus gamma square plus cos gamma t plus beta minus cos omega t plus beta. I have written here a dash, we have written here a dash because we have done some trade-off here, taken some term inside, so that we want to look at what happens near the resonance. Now at the resonance, gamma will tend to omega, so we do the d gamma by d omega of this term here, the second term here, and take gamma tending to omega. So you will basically get x equal to a dash cos omega t plus alpha, the small f by 2m omega t sin omega t plus beta. So thus in resonance, the amplitude of the oscillation increases linearly but with time, and this increases linearly till the time when the theory becomes invalid, because we are only interested in theory of small oscillations. So far so good. So now we try to do this in the complex form. Now we write x as a exponential I omega t plus b into exponential I omega plus epsilon t. Now clearly this term is slowly varying compared to this one, because epsilon is very small compared to omega, because omega and gamma, they are of the same order. So from here you compute the value of c, and you can see that c varies between mod of a minus b to mod of a minus b to a plus b, or mod of a plus b. This phenomenon is something which is called beats when you have two frequencies in the problem. Now we take a special case, and we take a special case of what? Okay, now we try to integrate the solution. So we write x double dot equal to x double dot plus omega square x equal to ft by m. This thing can be written as d by dt of x dot plus, we write one extra term I omega x, and to offset it we add minus I omega x dot here plus I omega x equal to ft by m. Now what we do that we write x dot plus I omega x as xi, and so your equation become d xi by dt minus I omega xi equal to ft by m. Now the solution of the homogeneous equation can be written as xi equal to a exponential I omega t with the corresponding constant a. The particular for the particular case we solve the solution, and we get xi equal to exponential I omega t 0 to t 1 by m ft exponential minus I omega t plus xi naught. The solution the solution will be the imaginary part of xi by omega, because here xi is x dot plus I omega x. Now the energy of the system is obviously not conserved because you have some driving. Now
And this part I think we can ignore because it's not clear. It's not clear. We have to read it further. So,
yeah, exactly.
yeah, okay. So thank you so much, Kishore, for the very quick revision and for explaining everything to us. And next time we'll do this oscillation of systems with more than 1 degree of freedom, which is very interesting. And until then, have a good time. See you.